Oh yes, so I was asked about the final homework. It's like the final lecture, and then so the because the homework work could be due on the presentation date. So I think it's natural to skip the homework, I guess. So there won't be the final homework. Okay, so let's get started. So today's topic is a bit formal in a sense that so we have been looking at toric code and the color code and so on. These are very specific type of codes, but today we are gonna treat more generic class of stabilizer codes, which are characterized by generators which are local. Of course, toric code you have interaction terms which are local, so that's an example of a local stabilizer code. But we will study generic properties of such codes, and so there will be lots of proofs and so on. And so for this, it's actually a bit difficult to predict the time. So it could be very short, or it could be very long. I don't know. But one thing for sure is we will be done at 5 for sure. So that's good. Okay. Right. Okay. So local code. But as I said, we will be studying local stabilizer code. But let us just start with some properties which holds for arbitrary stabilizer code. And I already put this in as a problem set, but I think it's nice to review it briefly. Certain duality in stabilizer code. So let's consider some arbitrary stabilizer code. This could be anything, like any stabilizer code. It could be trivial or toric code or color code. Anything is fine. With k logical qubits. And so let A and B, which is a complement of C, to be some subsystems. So it's just a bunch of qubits. So that A and B are complementary. So A and B covers the whole region. And we're going to define this GA be the number of independent non-trivial operators. Then the following formula is always true. So always equals to 2k. Okay, so this was the result. So now I guess not everyone has solved the homework, so I guess it would be nice to give a little bit of examples. So again, imagine the toric code on a torus. Then we have this square lattice, 2 parts identified. And suppose that we pick some trivial region which can be shrunk to a point, and its complement. Then we say that A does not support any logical operator because this is topologically trivial, and the logical operator needs to wrap around the torus. This means that the GA will be equals to 0. Here we are counting non-trivial logical operators, so identity operator is not counted. But if we look at B region, then we can support all kinds of strings. So you can think of X string, Z string, X string, and Z string. And there are 4 of them. 4 means that's an independent generator. So, and the toric code has k equals to 2. So you see that okay, so that's good. And another example is this. So B is this complement. And in this case, you can define a string of X and a string of Z here. So GA is equals to 2. But B is again another like string-like region where it's very wide string. But so you can support these 2 logical operators. And then therefore ZB is equals to 2. And then okay, this is equals to 4. So this formula holds. But the point is that this type of formula, GA plus GB equals to 2K, is true for any bipartition in a stabilizer. Now, in the homework, I guess we proved this result by using some technique using mutual information and so on. But today, I'm going to give you some simple proof by using the properties of a stabilizer code, especially algebra of Pauli operators. So this is another version of the proof. So okay, so we have some stabilizer code defined, and I'm drawing square on a bunch of qubits, but it doesn't need to be 2 dimensions, but just illustration purpose, and split it into two parts. And let's assume that this supports NA qubit and NB qubit. Of course, NA plus NB is equals to total number of qubits. Now, the important observation is that there are n minus k independent stabilizers. Okay, and of course, this choice of a set of independent stabilizer generators is not unique, but it turns out that you can choose these stabilizers in the following way. So this is A region and B region, and then some of the stabilizer operators have some non-trivial support on A, but it acts as an identity on B. So this box just means that some Pauli operators which are not identity. And some of them can be written in this form, where it's completely supported on B. So I guess these things can be defined. These things define the stabilizer subgroup of stabilizers supported on A and supported on B. But of course, there are some stabilizer generators which are non-locally supported over A and B. Okay. And this choice is a bit ambiguous because if this is a stabilizer which is non-local, then you can actually multiply this stabilizer with this stabilizer and it's still non-local. But well, the point is that you need to choose independent stabilizer generators. You can arrange them the following way. And let me just label the number of generators in the following way. Just SA, SB, SAB. Okay. And then since there are k logical qubits, the dimension of S is n minus k. So there are n minus k independent stabilizer generators. So okay, so this is the case. Now, so what was logical operator? Logical Pauli operator in region A. So such operator, let me call it LA, for example. Then, first of all, LA needs to commute with stabilizer generators. Right? So what kind of constraint this would put? The answer is the following. So there are in total 2 to the 2 NA Pauli operators on A, right? And the reason why we have 2 NA is because, well, for a single qubit, these are all the Pauli operators. So this is the case with NA equals to 1. So it must be 4 to the NA, so that's the reason. But this constraint, so the point is that this constraint comes from these 2 operators that has support on A. So that is SA and SAB. SB, these guys do not do anything because it's an identity on A. Therefore, there are SA plus SAB constraints. And these 2 constraints, these constraints basically cuts the possibility of the number of possible Pauli operators by half. So there are such Pauli operators. On A. But commuting with the stabilizer generator is not the end of the story because logical operator LA is equivalent to another logical operator LA prime if let's see. If they are related by application by stabilizer generators. Now, LA are the operators defined on A, and there are SA generators of stabilizers which are completely supported on A. So for each LA, there are 2 to the SA equivalent operators on A. So therefore, we need to divide this number further by this number. So therefore, GA, so the total number of logical operator here will be okay. And this number is, of course, equals to 2 to the GA. Here, we are counting the number of generators. So you need to put it on the exponent of it. This implies that okay. Just very simple observation. But we can repeat the similar argument for B. So basically, you need to just replace A with B. Then the answer is okay. Now to derive that formula, we just add these two expressions. Then we get the following. Good. But the first term, this object, is 2n, then this object as a number of independent generator, so it's so it should be equals to 2k. So that's how you can derive this formula. Okay, good. So this is like another proof of this duality formula of a stabilizer. Any question?
Yeah. So by like the first argument, the number of independent non-trivial logical operators depends on the number of subsystems we partition the space into. But that, like the relationships break down if you partition it more than two spaces.
Right, right. So it must be A and B. So it's a bipartition.
So how we define the space changes the stabilizer code with toric codes?
So how space?
How we define the space changes the toric code.
So in the case of the toric code is made of a bunch of qubits, right? Then you just think about set of qubits. You declare that, yes, as an A region, you just want to specify a level of qubits you want to include in A, and then all the qubits it's not included in A becomes B, the elements of B.
So, okay, so it's not that it actually changes, it's just that this relationship doesn't have some kind of equivalent to more partitions of space. Because the number of qubits in the system couldn't change just because we label things differently.
Right, right. So the total number of the qubits in the code is fixed, and then you just split n qubits into two parts in a way you want. Anyway, does this make sense, or is that the question?
Yeah.
You're asking, or?
Yeah.
Yes.
So we could apply this theorem repeatedly and say break B into regions B and C.
No.
And
it is true that if C region is smaller than the original B, then the number of logical operators should be smaller or equal. But if you have like ABC partition, then we don't have any generic formula.
okay, maybe I missed this. Which part of the proof breaks down at that for that?
Well, in that case, I would say that I haven't tried this carefully, but right, you probably need to add C here, and then you need to think about all possibility of stabilizer. There will be 7, but 7 means that like something like this, and all 4 others. But I haven't tried this, so at the level of proof, maybe you want to think about something like this. Then here, I want to pick generators so that the applications of other generators wouldn't change this generator to something like this or this. But this definition is becomes ambiguous because this generator and this generator could lead to this one. And then so there are some 3 possibilities kind of mixed with each other. So that could be one possible difficulty. But I'm not sure. That part maybe we can take care of. But again, for now, it's, I think, safe to say that it just applies to bipartition. Yes?
Maybe I'm missing something here. So far, I'm only seeing single qubit logic gates.
Single qubit logical.
Yeah,
Oh,
the X lines and the Z lines.
yes.
The usual winding number construction and so on.
Right.
Now, there are 2 qubits in there if you have a toric code on a torus.
2 logical qubits, right?
2 logical qubits. Right, so if I have 2 qubits, I could do something like a control knot, making one of them the control and the other one the target. What does that look like in this picture?
CNOT gate?
Yeah, between the 2 qubits.
In this picture.
Or a control Z if that's easier to construct.
So in the toric code.
Yeah, I've got 2 qubits in it. I can do a 2 qubit option.
It's actually a very difficult question because like there's no transversal gate for the toric code. Any Clifford gate except Pauli's. And then you can try this shifting trick, that is you apply Hadamard, which changes vertex operator XXXS to ZZZZ, and if you shift it, you return to the same code. And that, I guess, will be like CNOT, I think. Yeah, I think it's CNOT. And
Missed it. It's just not been covered in this. Right, okay.
or it's just a very different question, right? So right, I say CNOT gate. Oh, you're asking like where it is supported, right? Okay. Okay. Now yes, I see the question. Yes. Right. Yeah, that's actually the topic of the lecture like next week. But there is a very nice result by Bravi and Koenig that proves that. So in this 2-dimensional picture, let's say this is toric code, but you can imagine something more like color code or something. And then it turns out the Pauli operators are always living in like a string, and then any Clifford operator, which is not a Pauli, must be a 2-dimensional operator. And there is like dimensional structure. So it's called a Clifford hierarchy, maybe. And then a higher level of the Clifford hierarchy requires higher dimensions, and there is some interesting trade-off and so on. And then there are some proof techniques you can use. Now this is a very, I think in some sense this is a simpler version because we only look at Pauli operators. And now when it comes to Clifford gates and so on, it's a bit difficult to define the number of gates and so on because it's overcomplete. So we need more other kind of techniques. Okay, this is the formula. Okay, right. Okay, so now, well, it's just an abstract formula, but it's so generic. So I think it would be nice to talk about a few applications. And I say it's application, but this result was more actually much stronger, which is called the quantum singleton bound. And singleton bound does not consider stabilizer. It's much more general. It applies to any quantum codes, but by using this formula, you can, this kind of thinking, you can derive this easily. And again, the way I derive this bound is probably not the most elegant way, but it's actually the way of thinking I'm introducing. We will use it later in the lecture. So let me do it. So singleton bound, probably Daniel has proved it, I think. Is it? Yeah. By using reference state and so on, and, subadditivity and so on. But this is a bound, so that's some combination of NKD. The way we can prove for the stabilizer code is just we split the system into 3 regions. Now, we're going to take A to be a region containing D minus 1 qubits, and then B, D minus 1 qubit. B, yes, okay. Then here is the rest of the system. Now, A is smaller than B, B is smaller than D, small d. Therefore, A is equals to 0, B is equals to 0. But this means that GBC, which is a complement of A, must contain all the logical operator. Now we observe that, well, region B had no logical operator. But now we think of like adding extra qubit one by one, one by one, one by one, one by one. Then we eventually have all the qubits defined on BC. Now the claim is the following. So given such a bipartition, ABC, then the volume of C must be larger than K. And the way you can prove this is that there are 2K logical operators. So this region C and region B. And then we know that all the logical operators can be supported on C. So let me just write it like this. Right, I mean, I just listed all of them. The assumption is that they are all independent. Now, suppose that C was actually smaller than K. Okay. Then now important point here is that there is no logical operator on B. So this where is it? Oh, I see. Choke?
Yeah, you have a green piece over there.
Yeah, I thought I had yellow somewhere.
Before.
Is there a blue piece over there?
So this is blue. So I think.
I don't know what happened to your yellow one.
Yeah, I had yellow, right? Because
Yeah.
there is a proof. Oh yeah, why ended up? It's a mystery. Well, I mean, even though I have a colored chalk, I don't do anything fancy. I just wanted to say that this is not identity. Okay. Anyway, so the reason why J are not identity is because if they are identity, it could be supported fully on B. But we know that ZB is equals to 0. So it should not be the case. But now we have L1, L2K. These are some Pauli operators. Again, there are only 2K independent Pauli operators. This is a region C. So there are only 2C independent Pauli operators. But there I have 2k Pauli operators which are not identity. This means that by combining these of them nicely, I can generate an identity operator. And then this means that there exists a way of taking a product of these logical operators such that it is living on completely on B, which leads to a contradiction. Therefore, yes, so this assumption was not correct, and this thing can be proved. So, right. Now, if we know that this is k or larger than k, then n must be larger than k plus 2b minus 1. Then you can derive the singleton bound. But later in the lecture, we are going to use this version of the singleton bound, not this version, but this version. Anyway, yes, so that's how you can prove this well-known result. Another important application of this idea is called the cleaning lemma. It's called cleaning lemma, but I mean, there is no distinction between lemma or theorem, I guess. But somehow this one is called cleaning lemma. So let's think about the same situation, arbitrary stabilizer code, and with any number of qubits and any number of logical operators. And then if there is no logical operator, on A, then B. Okay. So again, this is very trivial because, well, if GA is equals to 0, then this implies that GB supports all the logical operator. That's it. Okay. So the reason why this is called cleaning lemma is following. Suppose by looking at stabilizer generators of your code, somehow you were able to guess that, so this is region A and the region B. Suppose that you are able to find some expression of logical operator, like living in this region. But this lemma says that it turns out that if A does not support any logical operator, then all the logical operators should be able to support it on B. This means that there is some procedure which probably just, in many cases, just applies some local stabilizer generators near the boundary so that there's some new logical operator L prime supported fully on B so that L prime is equals to L in the code word space. So in this sense, the support on A, this part, can be cleaned by applying some stabilizer generators nicely. For this reason, this lemma is called a cleaning lemma. Yes.
So why can't we do it the other way around and push the boundary of B, the boundary inside B into A instead?
Right. So this is very important. We are assuming that there is no logical operator supported on A.
Just none at all, or no?
No, not at all. Not at all. So in the case of the, again, I think it would be nice to look at the example that is the toric code. So let's do the toric code. In the toric code, this tiny patch of the region is a region which has no logical operator. Then B supports everything. But now the point is that if you find a logical operator somehow by looking at the code, then find that, okay, this looks like a logical operator. But it turns out, as we know, that we can always define this logical operator in a way that this avoids the region B by applying stabilizer generators. And this avoiding can be done by applying stabilizers around here. So for this reason, this is called cleaning lambda. So there is a very, sorry. Why? I shouldn't. Sorry, this is it's not a good mistake. A and B. So there is a imbalance between A and B. It's not symmetric. So we are assuming that there is no logical operator on A, and then in that case, B supports everything. Okay. Maybe one another comment I can make is that to just make some connection to error correcting code. Yes. So suppose that there is some erasure error. On A happened to my system. That means like someone came to my laboratory and then just remove all the qubits on A region. Then the point here is that, well, GB is still 2K. This means that by measuring some representation of logical operators will allow me to recover the information, right? This means that this GA equals to 0 means that recoverable. Okay, and that is precisely because if we have a logical error, or no, qubit loss error on A, you can clean the logical operator out from this region A so that you can define a the same logical operator outside region A. And this logical operator has no contamination. It's defined on the qubits that are remaining in the system. So by measuring this logical operator, you can get the encoded states. This is like the implication of the cleaning lemma. Okay, so that's the cleaning lemma, and then so will be very important. Are there any questions so far? Okay. All right, so now maybe this lemma sort of is more generic than cleaning lemma, so I'm gonna keep this slide probably. And right, so now as I said, that today's subject is local stabilizer code, but so far we have been talking about some properties which should be true for all the stabilizers without any notion of locality. But now let's see what happens if we have local stabilizer codes. So I need to sort of define what I mean by local codes, but I don't want to be super rigorous, but it would be nice to have some definition. Local codes. So I'm going to illustrate the definition in two-dimensional system. consider a two-dimensional square lattice. And we place qubits of vertices. Okay. And there are L by L qubits. And we assume that this L is a very, very big number. And by big, I mean the following. We will be thinking about family of a quantum error correcting code with increasing value of L. So there is a formal way of taking the limit of L goes to infinity. That is a precise mathematical meaning. But we can just imagine that L is a very big number, roughly. Now, we are going to assume that SJ, stabilizer generators, are geometrically local. By which I mean the following. You can always draw some finite size box. So in this case, it's a 4x4 box. But in general, we can say like W by W box. And then we assume that SJ operators can be supported. W by W box. And here it's important that W is order 1 number. By order 1, I mean that the difference is of course L, and this stays finite. Now, this defines the local stabilizer code, and you may ask why I'm thinking about only square lattice. But the point is that, well, toric code, you can sort of embed it into a square lattice, right? For example, I can consider lattice like a little bit bigger space, and if I use these qubits living on edges of this bigger lattice, then that's a qubit lattice for the toric code. So the point is that with this square lattice or hypercubic lattice framework, you can basically treat all the lattices which has a low density or fixed density per volume. Then now we can formally think about Hamiltonian realizations by putting all the stabilizer generators in the Hamiltonian, but only the local. Okay, so this is the definition of local codes. And so this definition, of course, allows a huge class of quantum error correcting code. So as I said, L should be taken very big compared to W. But in principle, you can take W to be 100 as long as L is like millions and so on. So the point is that there is a very well-defined way prescription of taking L goes to infinity. That's the important thing. Okay. Now, are there any restriction on the coding properties on stabilizer code by limiting our attention to this SJ being geometrically local? So for example, this very beautiful singleton bound, it doesn't assume anything about stabilizer code. It actually applies to any codes, but let's say if we put some constraints on locality of the generators, what's going to happen? And okay, so It turns out there is a very non-trivial upper bound on the chord distance of local chords. So let's consider arbitrary here capital D is the spatial dimension of the system. So toric chord, it's capital D is of course 2, but you can think about 3D, 4D, 5D, 6D, and so on. And then it turns out that the following bound is always true. Okay. Where small d is the chord distance. So this is pretty non-trivial because n is L to the d. So this result says that, well, actually distance cannot be as big as the volume of the system. It's only an area or the one dimension lower in the system. And this makes sense, right? Because in the case of the toric chord, you have string-like operators. So it's defined on a one-dimensional lower subspace. But this kind of result can be proven in a very generic manner. So is there any, yes?
So you said that instead of having a square, we could deform it to like a rectangle by just taking different subsets, right? So doesn't that imply that all the local SJs have to be of the same geometry, just scaled down as their total lattice?
Right. So rectangle, I see. Right. So the point is that well, I had more. What I had in mind is more like if you have a hexagonal lattice, what should I do, and so on. Then the point is that just using a subset of qubits from the square lattice, you can represent hexagonal lattice and so on, right? So that's what I.
So then, do the SJs also have to turn into hexagons, right?
Sort of, but the point here is that by this procedure of using only subset of qubits, the value of W could increase a little bit, but it stays finite.
Sure, the value stays a certain value, but does the geometry of the shape change?
Yes, but the important thing is I'm picking this box to be any region which contains SJ.
Okay.
So even if SJ shape changes, it doesn't matter if I have like sufficiently big but finite box. So that's okay, so let's prove this. Now, well, so I'm gonna show you the proof for capital D equals to 2 because higher dimensions are pretty easy to prove once you understand this proof. We are gonna choose A and B to be some union of a smaller region, AJ and BJ, and we are gonna choose them in the following way. So here's A1. Next, you have B1, and then A2, B2, and then keep repeating it. Then, some point you have AM and BM. Okay, so it's just an alternating manner. But important thing here is to pick these regions so that it has a nice width, in a sense that well, stabilizer generators are supported in the following way. They can act only up to 2 regions, not 3 regions. And this would be, of course, possible if we take this to be W or slightly bigger than W. Okay, now let's use this result. GA plus GB is equal to 2K. This implies that at least well, if you sum up two of them, you should get some number which is larger than 0. So at least one of them is non-zero. And without loss of generality, we can assume, let's say, GA is larger than 0. Right? This means that there exists some logical operator which can be written in the following way. This is LA1 times A2 LAM, just tensor product of a bunch of them. So the point is that this operator L is supported on this region, this region, this region, and this region, but only on A part. But now here the important observation is that if L is a logical operator, which means that L should commute with order Sj. But the point is that there is no stabilizer generator which acts on these two parts simultaneously. This means that LA1 should commute with A, LA2 should commute with, and so on. So this means that all this LA1, LA2, LAM satisfies the criteria to be a logical operator. But of course, some of them could be just a trivial logical operator, right? Some of them could be identity operator. But the point is, because L is a non-trivial logical operator, so at least one of them, LA1, LA2, or LAM, should be a non-trivial logical operator. So suppose that, okay, I think I can. If this LA1 is a non-trivial logical operator, then it is supported on region with W times L qubits, right? Width is W and then the vertical length is L. So this implies that there is a logical operator which is WL body, so distance must be at most WL. So that's how you can prove this result in two spatial dimensions. Of course, if you want to generalize this to 3D, then what you do is yes, then this is A1 and so in an alternating one. Then you can show that supported W times L to the D minus 1 qubits. So this is how you can derive this bound. Okay. Any questions? Good. All right, so Now, if this is fine, then I'm going to just make a few comments on the interpretation of these results and just mention several open questions that has been bothering people. That is something called a self-correcting quantum memory. So let us again briefly remind ourselves about the classical memory, such as classical ferromagnet. So the Hamiltonian of the classical ferromagnet, or just Ising model, can be written in the following way. So spins should be in the same direction. Now let us consider this classical ferromagnet in two spatial dimensions, so that we have these spins, and then spin must be aligned in one direction, all up or all down. So that's how you can encode the classical information. So this is basically a magnet. But the point here is that this classical ferromagnet is actually a stable memory at finite temperature. So when we talk about cold word subspace, and so we typically think about zero temperature subspace, mainly ground states. But imagine that we put this system of classical ferromagnet in contact with some thermal bath, like this room. Then you will go to some excited states. But the point here is that one of the cold word is all zero state, the ground state, and the other cold word is all one state. So in order to go from all zero state to all one state, you actually need to create some excited states, let's say which would look like, so you start from all zero state and just create some excitation by flipping these 4 spins. But now this configuration costs a lot of energy, because here you have violation, here you have violation, violation. So along these lines, you have energy violations. But then if this system is very, very big, then at some point, in order to go from all zero state to all one state, you need to create some very, very big island of ones and zeros. But this is ferromagnet where your spins wants to be aligned. So there is an energy penalty here. So excitation energy is kind of lower bounded by this length L. Now, in order to go from all zero to all one, this island of ones surrounded by zero should become as big as the system size. This means that there is a kind of energy barrier which is order L, right? But order L energy barrier is very big. So if you have some energy spectrum, then bunch of excited states. This is O0 state, and this is O1 state. Then my thermal environment, well, thermal environment can couple to my system only locally, so it will flip spins only locally. So it will try to increase the energy a little bit, but there's some hidden large energy barrier, which is order L. Then climbing up this hill is very difficult. And the natural thermal dissipation process induced by the thermal burst will try to return the system to the original encoded state. And there is some small probability of hopping from 0 to 1, but this is basically exponentially suppressed. So for this reason, memory time is exponential. Okay. Well, it's actually you can estimate the memory time in the following way, that is exponential energy barrier divided by thermal temperature T. And then this is L, so it's a very big number. Okay, again, this is the reason why we can just bring our classical memory or magnet here in this room, and the information is still there. Okay, that's a classical ferromagnet, and that's why we can securely store information very easily. But can we do something like this in the quantum error correcting code? And this is a question. And it turns out that this is a very difficult task. So this is called a self-correcting quantum memory. Okay, so the reason why we say it's self-correcting is because thermal bursts sort of do the error correction for you without telling it how to do it. And that's why we use this word self-correcting. But more precisely, basically, this asks whether the quantum memory works at a finite temperature or not. Now, one good candidate of this good quantum error correcting code is, of course, 2D toric code. But unfortunately, this 2D toric code is not self-correcting memory. The reason is the following. If you have the toric code, then if you apply some string of Pauli operators, you can create a pair of anionic excitations. In this case, it's electric charges, but this labeling does not matter much, but you have some excitations. And this excitation basically costs only finite amount of energy. That's energy 2. What? Wait, just object. Now, you can move this excitation freely by using this string of Z operators. Then, starting from the ground state of my system, this process of implementing the string of Z operators, physically that corresponds to creating a pair of anionic excitation and then wrapping around the torus. This process has energy barrier which is just order 1, right? Because throughout this process, we don't need to create large energy state, not like that one. As a result, it turns out that the memory time of the toric code is just order 1, in the sense that you just need to stick this O1 number to this delta barrier. It's just a memory time is order 1. And you can make this argument very rigorous by using some well-defined model of a thermal bath and so on, but this is the observation you can have. And this is very bad because in the case of classical computers, we are able to just use memory without doing any error correction. And storage is very straightforward. But in the case of the toric code, if you prepare a quantum state into some one of the ground state, say, then let it evolve on the thermal bath interaction, then the information will be lost completely after order 1 memory time. So that's pretty bad. So what should we do is, of course, we need to perform quantum error correction before the information will be dissipated. So basically this quantum memory time tells you how frequently you need to perform quantum error correction. This crucially depends on how high the temperature is and how is the coupling to the thermal bath and so on. But strictly speaking, this two-dimensional toric code does not work as a self-correcting quantum memory in the presence of thermal bath. That is a statement. So this is a bit unfortunate story, but yes?
Well, could you explain again the O1, how you see it as O1 and the energy barrier is O1?
Yeah, 0 and 1, yes. And oh, you mean this one?
No, I mean on the bottom here. It said this. That.
Oh, the Y, the energy barrier is
yeah, this picture and relate to that one.
Right. So we are defining the energy barrier as the following. That is, you start from one of the code word state and then move to other code word space by applying local Pauli operators. Then in this case, the strategy would be just flip all the spins. But if you do it one by one, then in the classical case, basically you need to create a region of ones and then you need to grow them. So the energy barrier is as big as the system size because we need to create this domain separating 0 region and 1 region. But the question is, can we go from one of the ground state of the toric code to the other easily or not? Then the answer is yes, because if we apply this ZZZZ operators, then we can go from one state to the other state. Now, if we think about implementing this Z operator sequentially, like Z, then this is just same as creating 2 excitations and then moving them. Then once you create the excitations, then there is no change of the energy. So then there is no energy barrier.
And creating the excitations is O1.
Order 1, right.
Oh.
Unless you put some very, very big number in front of the Hamiltonian. But that's sort of cheating, right? So that is the question. Now, I guess the story you can tell from this result of the code distance of local code is that we have seen that in 2 spatial dimensions in the stabilizer code, there must exist some string-like operators supported on this A1 or A2 or this one of this strip. But if you have a string-like logical operator, then so the point here is that we created excitation by cutting the string-like logical operator into parts, and then its endpoint created excitations. So this implies that this string-like logical operator, no matter how we construct string-like operator, maybe it's not like Z, but it could be like more complicated, and it's a bit more fatum, like W. But the point is that excitation is localized around here, and then the amount of excitation, the excitation energy stays finite. So energy barrier will be order 1. As a result, such a 2D stabilizer memory is not a good self-correcting quantum memory at finite temperature. That's something you can sort of prove. Okay, so that's a kind of unfortunate situation, but still it's just 2D. So we can be optimistic and then try to go to 3D, 4D. 4D is, I think, too optimistic, but right. So higher dimensions, and then it turns out that okay, I'm not gonna go into details, but so far the only known example of self-correcting memory with rigorous proof is the 4-dimensional toric code is self-correcting. Okay, that's good that such a thing exists in this world. Well, which world, I don't know. But the question is 3D. Then we still don't know the answer. And so this problem remains open yet. And there have been several interesting proposals of self-correcting quantum memory in 3 dimensions. And actually one of them, which is called the Fracton topological order or cubic code or Haar code, which was very interesting model which goes beyond these theories of toric code, and it's a kind of new topological order and a very interesting toy model. But in a very strict sense of self-correcting quantum memory, all the proposed models of local stabilizer code in 3D, it turns out they have the finite memory time at finite temperature. So in this sense, none of these models work as a self-correcting quantum memory. But in practice, they may work in actual situations, but in a strict sense, they are not self-correcting quantum memory. So this problem remains open at this point. Good. Yes?
No, I guess also back to my question I asked before. Like, you don't need 4 dimensions to implement a 4D toric code. Like, you can implement this in like
3D and then a little bit of non-locality. Yeah.
So then, like, I thought this one had to do with intrinsic topological.
Yeah, so you're asking two questions, right? I mean, 4D, we could simulate it in 3D. Maybe, yes. But that's probably a more like engineering question that I do not know the answer. That might be possible. There may be some clever techniques to do that. But such a strategy is not scalable in the sense that, well, 3D toric code, in principle, 2D toric code, 3D toric code, in principle, you can build it in the lab and you can, if you have enough resource, you can enlarge it into like 1 million by 1 million, 1 million. But 4D toric code, if you want to simulate it with 2D lattice or 3D lattice, you cannot do that, right? So there is some non-locality. So that's the question. That's the point. And then, yes, as you said, well, this is an intrinsic topological order. So you can think about symmetry protected kind of a quantum error correcting code. And that might work, like, for example, Majorana-based quantum error correcting code assumes that well, you can create a very clean Majorana system which have a fermion parity protection. That may be possible with very clever engineering, and then, but again, in a very strict sense, if environment does this one error of breaking the parity locally, and globally it must be protected, but you can break it locally, and then the information will be gone, and then that's very bad. So yes, that's now the question is like what kind of physical systems you want to look at. Okay. Okay, so I think it turns out that it's taking longer than I expected, but now it's, I think, a good time to take a break maybe. So we can take a 10 minutes break. Okay, so right, so it's actually today I prepared three subjects or three things to prove, but I was planning to spend 1 hour each, but since I think it's going a bit slow, so maybe we can just skip the second one. But maybe I can tell the second thing we were proving. That is, we have been talking about self-correcting quantum memory. That is dynamical properties. That is, you couple the system to the thermal bath and then ask how long does it take to destroy the encoded information. And but can we make this definition more precise? And then one idea is that, so in the previous lecture, we have learned that, well, if the system is a quantum error correcting code, such as the toric code, then it turns out that it takes very long time to prepare the ground state or code word space in the sense of the circuit complexity. So maybe we can use a similar idea for this self-correcting memory. And then one proposal by Hastings is that we look at this low beta, the thermal Gibbs ensemble, and then ask if it is easy or difficult to prepare this thermal Gibbs ensemble. By easy means that we start from some classical ensemble and then try to create this low beta. And if you can do it in a short depth circuit, then well, it's easy, it's trivial. But then if it's very difficult, then it will be like topological order at finite temperature. So that was the criteria he proposed. And then he showed that the 2D toric code we mentioned is actually not thermally ordered in this sense. That is, there is a very efficient way to prepare Gibbs ensemble for 2D toric code. But for the toric code, actually there is no such easy way to prepare Gibbs ensemble. Okay, so that was the kind of the thing. Yeah, which is, I think, something very important in recent developments. And it's actually the similarity of this thermal Gibbs ensemble seems to be very important in many different contexts. And I was told that it's actually this efficient preparation of this thermal Gibbs ensemble is very important in a recent result by Fernand Brandau and others. I forgot. Yes, Krista. So they say that well, semi-definite programming, you have a quantum speed up, provided that it's actually the thermal Gibbs ensemble preparation is efficient. So it seems that this kind of way of thinking has more applications and so. But anyway, that's the minor comment. Anyway, so let's move on. So we have proved one result, that is a upper bound on the code distance. But when we talk about quantum error correcting code, there are three important parameters, n and k and d. And so this is the bound on d. And then next, we want to talk about the bound on k, the number of encodable logical qubits. Okay, so the statement we are going to prove is the following. So consider to the local code, then the claim is that following. such a bound should hold. And okay, so the lattice is L by L. Now let's first look at the example, and of course it's the toric code. And the torus. And let's see, k is equals to 2, and distance d was equals to L. So logical operator like a string. So if I plug this thing into left-hand side, you get that this is L square. So it's of course upper bounded by all the L square quantity. So it seems that the toric code is saturating this bound. So the point is that in this problem, you are allowed to design your stabilizer generators in a way you want, in any way that SJ are local, but no matter how you design it, actually this bound should be the case. This is the result. Now, we want to prove this result, and then the proof is actually pretty elegant, and there are basically 2 steps. Okay, this is the lattice L by L, and we are going to split the lattice into the following regions. Okay, so some nice pattern. And the point of this partitioning is the following. We can assign 3 color labels, A, B, C, so that A is like a face, B is like edge, and then C is like vertices, sort of. And then A, B, 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 B. Well, I'm not going to repeat this. Well, maybe I can. Okay. And here in this partitioning, it is important to take the this ABC region to be sufficiently big so that oh, no, this is C. So that these local stabilizers may act like this, but this is not allowed. So there's no stabilizer generators which act on the region with the same color, A and B, A or B, B. And this can be done by picking this region width, like W, or slightly bigger than W. So the reason why we wanted to do this partitioning is precisely because the following. So, stabilizer generators are the same level. Okay, it's good. So now this kind of partitioning is actually a very powerful proof technique, and it actually can be used in many different contexts. And in our context, actually, we are going to take this region, tiny region, AB, this region, to be roughly d over w. D is the chord distance, but slightly smaller than d over w. Okay. The reason why we want to take the region to be sufficient, so this maybe it's a bit too small to see. In the following. So the proof is two-step. First step, we can easily prove that this C is equals to 0 because C is such a tiny region, and then this length is basically D, and it's much smaller than D, so because C is smaller than D. Similarly, ZB is equals to 0 because again, each B region is smaller than D. That's good. But it turns out this is a bit non-trivial statement we are going to prove later. But GA turns out to be 0. This is a bit non-trivial because the volume of A is actually order of D squared, right? Because it's a face and then D by D. But it turns out this can be proven. So this is the thing we need to prove. Will be proven. But suppose this is true. Then in this case, we can use the argument from the singleton bound. That is, we had the region GA, which is 0, GB is equals to 0, but BBC is equals to 2K. This means that by inserting C qubits into region B, suddenly we can support all the logical qubits. And then, by the way, this follows from GA equals to 0. Therefore, from the singleton bound proof, we have C, which is larger than K. But now, how many qubits are contained in C, the total region C? Then you see that there are number of these each tiny patches of this circles. This goes like 1 over these. Well, yes, L over D times the square of L over D, roughly, because at each length D you have one this square, so it's L over D to this 2 with some constant, which is basically W, but we are not that interested. So this means that L over D square must be roughly like this, larger than K. Then we have this result you can derive. That's how you can prove this result. Okay, so is there any question about this logic? Yes?
Okay, sorry. So by design in the leftmost picture, C is meant to be very small. Okay, so what exactly defines the length D over W? Is it the midpoint of one B to the midpoint of another B?
Oh, so if we want to be very strict about this, and then yes, so there's one subtlety in this construction is that I'm assuming the distance D is much bigger than the W. Then we can define these things unambiguously, and well, you can define the distance like number of qubits here, like D over W, or slightly smaller than D over W. Yes.
You need to sharpen up the rule for forbidden stabilizers, because if I take a bunch of stabilizer operations and do all of them, that's another stabilizer operation.
Right.
So maybe the statement should be, any operator you write down that looks like it's a stabilizer generator can be decomposed into stabilizers that act on at most.
Sure. So what's the
No, if you write down
local.
any operator which is
Local stabilizer generator. Yeah, but this.
Yeah.
Yes, so that's what I mean. So there is a choice of a local stabilizer, independent stabilizer generator, so that they do not talk to separated these subregions of the same color. That is the important thing. And you can actually try this kind of partitioning, and then in higher dimensions, and then you can prove a similar bound in higher dimensions. And this kind of technique is also actually very useful in deriving the result I mentioned, the Bravy-Koenig bound on the Clifford hierarchy. But anyway, so this is logic. So clearly one non-trivial statement here is that this GA is equals to 0. But why is that? Even though A is a very big region. And this statement follows from what the so-called I don't know why it's called holographic principle, but the authors decided to call it holographic principle. In some sense, yes, but so still, let's imagine these two-dimensional situations. And so here the system itself is very, very big. But we are going to pick some region. Three regions. And then this is a complement of PQR bar. Then, so when we say region, it's always important to take that the region, the width to be W, so that the stabilizers can talk to only neighboring regions. Then this lemma basically says the following. Let's assume that there is a logical operator. supported on this joint region PQR. And let's further assume that so let's call this logical operator L. Let's assume that the two regions L and R does not support any logical operator. Then it turns out only on P. So the reason why this is called a holographic principle is because if we have some logical operators like this, then it can be supported on boundary. So it's like hologram. So that is probably the reason for this name. And now with this lemma, I think you can sort of see why GA must be 0, because if you have a logical operator on A, then that could be supported by actually much smaller region B, which actually the volume is order D, not D squared. So I'm going to show this, the proof of this lemma just for simplicity. In the case that there's only one logical operator in my system, especially on PQL. Now this is just for simplicity. So the information I have is GQ and GR is equals to 0. Now, by using the duality of the stabilizer code, so we can derive this. Yeah, that's good. But now let's think about this object. By this object, I mean the following. Maybe I should draw it more obliquely. So this region is basically so the complement and the Q. Okay. But since we already know that Q does not support any logical operator, so just by appending Q wouldn't increase this number. So and when you derive this, of course, it's very important that there is no stabilizer generators, which talks local stabilizer generators talks simultaneously on Q and this region. But this would imply that Z P R equals to 1. But GPR is now a region which is P and R. So it says that GPR is equals to 1, so there must exist one logical operator. But we already know that GPR was equals to 1, so let's call this logical operator L. This means that this logical operator supported on PL must be the same logical operator. So this joint region supports L. But because, again, because of the locality of stabilizer generators, there's no local operators which talks simultaneously on P and R. And also GR is equals to 0. So appending R shouldn't increase the number of logical operators. Therefore, you can conclude that GP is equals to 1. So this means that if you had an operator on PQR, then you can sort of shrink the size of the logical operator into this boundary region P, like a hologram. So the logic was okay. Now, once you prove this result, I guess you can easily show that GA must be equals to 0. But well, that's basically by induction. But I guess it's a bit cumbersome to write down the induction very precisely. So let me just tell you how the argument should work. Well, I think it's almost clear, but it would be nice to. So basically, you will want to use this holographic principle in a hierarchical manner. So you have this big lattice, the whole system. Then you have region A. So this whole region is A. I mean, one with a patch of A. Then the idea is you split the whole system into smaller patches like this. Then let's call it AM, AM minus 1, and so on. Then the idea is from the interior, let's say starting from these three regions, you can use the holographic principle to show that there is no logical operator in these regions, and then you basically keep adding layers and layers, layers and layers until the volume of AM becomes order of D. That's the time you start to have some logical operator. Then for this reason, you can prove that GA is equals to 0. Is there any question? Yes.
Okay, so one minor question. In the proof of the holographic principle, so we union on the Q region in the last word algebraic line, right? And we say that there's 2k minus 1 in that downwind line.
Yeah.
Now, we union on the region Q, and we say that doesn't change the number of operators who are supported on that new region. So why couldn't we, from there, just union on the region R in order to immediately...
So, can you repeat from the beginning? Yes.
Oh, okay.
Yes.
So
this one?
We have the
Yes.
region outside of all three, right? And then we union on the region Q. And we say that there was no operators on Q in the first place, and so the number of operators supported on the union of those two places is 2k minus 1. So my question is, why can't we continue that logic in union on the region R and immediately say that because R unioning on R, which already has 0 logical operators supported on it, also conserves the number of logical operators on the complement of PQR unioned with Q unioned with R. instead of having to do the argument involving locality of operators on the two annuluses at the end.
Sorry, I probably still don't get the logic.
Do you want me to?
Yeah, please.
Oh, okay.
Yes. I mean, sounds plausible. So I mean,
So at this step we have this, right?
mm-hmm.
So why couldn't we also say that PQ R Q is also equal to 2K minus 1? And, instead of going from here to here, go with
Oh, right.
like shape that.
Sure. But I didn't assume that. Yes. I didn't assume that this is 0.
Okay. Yep.
Mm-hmm. That's this.
Thanks.
Then that is actually I mean, that's a good point, and then I kind of sketched this proof, but this is sort of in this induction step it's kind of important. But yes, so right. So any questions? Yes, good. And then now it's again a problem. I thought this part will take 1.5 hours, but I finished in half hour. It's hard to predict the time. So maybe I can just go back and then prove this thermal instability or stability thing very quickly. The problem is I yeah, but I think it's doable. So I might skip some steps because it could get a bit technical, but I will try to give you some essence of the argument. Okay. So let me just briefly remind you the motivation. So from the previous lecture, we know that quantum code, then is code words, and high quantum circuit complexity. Okay. But the fact that these two states has a high complexity is of course crucially related to the fact that error correction can be performed. But this is a statement that T equals 0, the temperature equals 0, by which I mean that we are only looking at the ground states, or code word space of the system. But the question of self-correcting memory is a question at finite temperature in the presence of the thermal bath. So then the naturally arising question is maybe this low beta, the Gibbs ensemble, has high complexity. But what does it mean by this thermal Gibbs ensemble having high complexity? And it turns out it's a bit tricky to define what it means by this Summer Gibbs ensemble has high complexity and so on. But for now, we just say that, well, the question we want to address is classical ensemble. Short depth circuit. This is the question we would like to address. And by classical ensemble, I mean the following. It's a example is you can just think about Hamiltonian, which are made of diagonal terms such as Pauli Z bases, and you generate some Summer Gibbs ensemble. We assume that the sampling of this classical part is very easy, and then having access to such a classical part, can we convert it into quantum Gibbs ensemble or not? That is the question. And so I'm going to show that 2D toric code is not summary stable. In the sense of this circuit complexity. And it turns out there exists some low-well depth circuit. Prepare. Okay. Summer Gibbs ensemble. And by the way, definition of the Summer Gibbs ensemble is just this thing. Yes. And you can prove this statement with full generality, but in this lecture, actually, we are going to do some simplified version. So, some simplification. Just make the argument simple. So the toric code, Hamiltonian, was able to, yeah, so we can write it like this, where like this. And it's actually, there's one technical subtleties I need to take care of, because it arises from the fact that these stabilizer generators are not independent, because and this fact actually adds one slightly non-trivial step in the proof, which are not that, I think, not that important. So just to avoid this problem, I'm gonna just assume that AV operator and BP operator are all independent by removing one of them. Yes?
Question regarding how does the self-correcting memory part relate to the quantum code and the temperature difference? So the quantum code, we're saying it takes high complexity to prepare the size zero inside one state, right? And here we want to show that you need high complexity to prepare the thermal Gibbs state.
So
What does it do with temperature, though?
Right. So thermal Gibbs ensemble is of course related to temperature, right? I mean, it is inverse temperature. And then if you take T equals to 0 or beta equals to infinite, then it turns out this Gibbs ensemble is just a maximally mixed state on the cold world space. So this definition of a Gibbs ensemble having high complexity is actually a natural generalization quantum called high complexity, because you can just take T equals to 0 and then it just says that creating a cold world is very difficult. It's just the same. And then, so again, let me emphasize that this sounds like a very natural generalization of the idea of like circuit complexity, or the characterization of the complexity of a quantum error correcting code in the presence of thermal bath. But at this point, there is no formal proof relating this definition of high complexity result to self-correcting memory. The problem is that the rho beta is a static property. There is no dynamics. This is just a given state. There is no dynamics. On the other hand, self-correcting memory, you prepare one of the cold world space, the state, and then couple it to the thermal bus, and then it's a dynamical problem. Like how long does it take to lose information, and so on. So it's pretty tricky to relate these two phenomena. But so far, this analogy seems to be working in a sense that if the system is not self-correcting quantum memory in a dynamical sense, then it seems that there is a way to prepare Gibbs ensemble very easily. And so the correspondence seems to be true. Any questions? Okay, so I'm going to use one simplification that is, so there are L terms, L square terms, but I'm going to consider only L square minus 1 terms, so that every terms are independent. Okay. But this is just to simplify the analysis. And now, I need to prove that there is a way to prepare this rho beta in a very easy way. I need to introduce one concept that is called the imperfect Hamiltonian. So the concept is basically the following. In the case of the stabilizer code, this is the Hamiltonian realization in the case that all the terms are independent. Now, I sort of want to consider an imperfect version of this Hamiltonian with some binary vector m in the following way. Where mj takes value 0 or 1. So it means that this means that this vector m tells you which term you want to keep and which term you don't want to keep. If this m is just vector with all 1, then we should keep all the terms in the Hamiltonian. But if it's all 0, then there's nothing in the Hamiltonian. So that is the definition of the imperfect Hamiltonian. Now, we would like to also define ground state space as rho n. So roughly speaking, rho m vector is the following object. you solve this Hamiltonian and then look at the ground states and then just think about maximally mixed ensemble over all the ground states. If this Hamiltonian contains all the terms in the original Hamiltonian without any missing terms, then this law is just a probabilistic mixture of all the ground states. But by removing terms, you sort of increase the dimension of the states, and it's a more and more mixed states. This is the construction. Now, I guess we have been using this property so many times, but this Qj operator, I plus Sj over 2, is a projector, which basically projects you into the ground state of the Hamiltonian. So this mixed ensemble actually can be written as following object. And okay, the following object. Now, maybe I can explain this a little bit. That is, when the Hamiltonian contains Sj term, which means that Mj equals to 1, then you need to project your whole Hilbert space into the subspace by using this projector. That is this part. So when you have Mj equals to 1, this part picks up this projector Qj. Otherwise, you just consider maximally mixed state, that is an identity. And this bunch of twos are important because trace of the density matrix must be equals to 1, while trace of the identity operator is 2 to the n. This is just a normalization factor. Okay. So this is the imperfect Hamiltonian. Now, the reason why we are considering this imperfect Hamiltonian is the following. It turns out this statement that the toric code gives can be easily prepared. Reduces to the following statement. So, so now let's take one of these imperfect Hamiltonian by picking up some terms from the this Sj and so on. But we do this in the following way. For each j with probability p, we take Mj equals to 0. So we just throw away some terms from the Hamiltonian. And with probability 1 minus p, we keep the Hamiltonian. Okay. So it's like erasure error, but at the level of Hamiltonian. So pictorially, it would look like this. So you have the toric code Hamiltonian, but some of this, let's say vertex terms. I'm going to only draw the vertex terms. are just now removed from the system, and the same for the placket terms. And this happens randomly. Now, the claim is the following. Most of this imperfect Hamiltonian are actually trivial, in a sense that there is a local short depth circuit which brings this HM into a classical Hamiltonian. Then for such classical Hamiltonian, we have, preparing a classical ensemble is free. So the point is that most of is very important in a sense that there is a probability of a very small probability that there's a 1 minus p to the n that we keep all the Hamiltonian to the system, but such a probability is extremely small. So for all the typical instances, this imperfect Hamiltonian is actually almost a classical object. And to prove this, is there any question so far? It's okay. So to prove this statement, actually you use some trick that is you split the whole system into a bunch of grids. Now let's assume that this contains V vertices. Just, count the number of qubits here. That gives you V. And now, no matter how small P is, if V is big enough, while it's constant, then there is a possibility, there is a very non-negligible probability of having one missing vertex.
Wait, sorry, what is the P dictated by?
Sorry?
What determines the probability?
Right. So I haven't specified P, but it turns out that in this problem, we should take P to be, what was the actual value? Yes. Some probability decided by the temperature. Mm-hmm. But for now, we can just assume that P is some small but finite number. Right, so just to recap, we have the toric code Hamiltonian. Then we just randomly remove some of the terms in the Hamiltonian with probability P. Now, if we take this grid sufficiently big, then we are almost sure that there must exist at least one missing vertex term, right? Because, we need to be very lucky that there's no missing sites inside this region if V is very big. But we can do this without taking V to be very big as system size. We can do it with some finite size. It's actually, in order to suppress errors and so on, it's actually, we would like to take this region as big as log L, but that's just some technical statement. But the whole point is that if I'm given an imperfect Hamiltonian, it is very likely that there is some missing sites, missing vertex operator. And by generalizing this argument, there is it is likely that we have some finite region with no interaction terms in the Hamiltonian, no SJ in the Hamiltonian. That can be done by picking this grid sufficiently big. So inside this circle, there's no term. Now we use the trick. Actually, we is a kind of similar trick, but we draw such grids. Like this. Then now the point is that in this toric code, the terms are local. So my stabilizer generator will be living like this, like this. But the important property is that no stabilizer generators, AV and the BP terms, 3 regions. Okay. Then it turns out if this is the case, then we can sort of coarse grain the whole system and view this entire object as one particle. Then my whole system looks like one big particle, one big particle, one big particle, one big particle, and where two local. So it acts on like this, but there is no such non-local interactions. Now, there are 2 different ways to proceed, but one abstract way to further proceed is that it turns out when Hamiltonian, 2 local, and commuting frustration free, which includes the stabilizers. So maybe I can just 2 local stabilizers. Then there exists some local unitary to bring HM into classical form. And you can sort of see this, that if you only have 2-body interactions, what you can do is you can actually create some EPR pair between neighboring sites, or you can create a ferromagnet by putting ZZ interactions and so on. But you cannot do anything else with these 2 local commuting stabilizers. That is one way of proving it. And another way of proving this statement is that you can actually prepare some encoding circuit for the toric code. Then it turns out because of this bunch of missing sites, the complexity of creating HM is actually at most as big as complexity of creating a toric code inside this box. That's something you can easily prove. And so that is the statement. Is this clear? Yes.
Okay, sorry. So the yellow regions in the big square, those are clusters of missing vertices?
Right. This white regions are the clusters of missing vertices. Yes.
So why do we know that they're going to be clustered together within each sub-region?
Clustered together. Oh, okay. So we pick some finite island, like white dot-like regions, sufficiently big, like just like vertex, and then we need to show that there is no interaction terms which are fully supported on this region or overlapping with this. And then, I mean, this is just some probability, right? then we can always find such a region if this patches, the grid is very big. But this is again a typicality argument in the sense that there is a very unlucky or lucky situation where we didn't lose any term in the Hamiltonian, but that's exponentially small.
Okay. And then, so to go from the grid with the multiple colors to the one on the right, you said we like coarse grained kind of, and like.
Kind of, yes, yes.
So if we're coarse grading, does this break down at like criticality where you have like scale invariance?
Oh, yes, coarse graining is just, I'm saying is that there are a bunch of qubits living in this region, in the finite number, that I can just view it as a very big spin with big inner dimensions. That's all I mean. So in some sense, this missing site acts like a part which is severely damaged by a thermal environment. So if at low temperature, which means beta is big, then P is very small, so such an island, such missing sites do not appear much, but it's still such a thing can appear, and then we use these parts which are severely damaged by thermal environment to create this simplified lattice to show that this object is very simple. And I'm not going to go into details of the proof of this, how to do this, because it's actually I need to study like things case by case, and it's a bit complicated. But the statement is that just two local Hamiltonian cannot create anything interesting if they are commuting. Okay, so I sort of started from this question of Gibbs ensemble and then suddenly introduced this imperfect Hamiltonian. So I think the final step is to relate this to these two ideas, and then and for this, this is just a very simple calculations, and so Gibbs ensemble is defined like this. But it turns out that there is a way to rewrite this thing in a nice way. Okay, so the left-hand side is a definition of the Gibbs ensemble. And we want to create it, and then it turns out that we can decompose it into the summation of this object. And what is this object? Well, first, rho m is just this maximally mixed ensemble in this imperfect Hamiltonian. So this ensemble in HM imperfect Hamiltonian. Now, this probability function is basically the probability of getting this imperfect Hamiltonian in this construction. And the probability is given by this number. And this is something you can pretty easily derive by using the fact that so you basically want to compute this object, but you have this Sj equals to square equals to I So this is an exponential function, so you just expand it in terms of like Taylor expansion and then massage it a little bit and then using that definition of rho m and then you can cast this into this form. Okay, so just let me summarize the logic. So we wanted to study if toric code is summary stable or not. And then one possible definition is, can we create Gibbs ensemble rho beta easily or not? Now we observe that the Gibbs ensemble can be decomposed into the following form. Now it's a probabilistic mixture, but the claim is most of the contribution in this Gibbs ensemble actually comes from imperfect Hamiltonian with the following property, which can be brought to a trivial form very easily. Of course, some of the rho m is highly complex. One example is, of course, the case we didn't remove any of the Hamiltonian term. But most of the terms are very simple, so you can prepare easily. Now, you may ask, like, is it okay to summing up all these probability distributions? And the point is that it should be okay, because if you have the toric code, then with a bunch of qubits, you can sort of insert ancillary qubits. Then for this ancillary qubits, you basically encode information about M. And then you prepare this M with M state with this probability M that's drawn from this function. And then you just trace out this environment answer, then you can create this state on your system. And then this answer can be sort of viewed as an environment which are causing trouble to you. It's a summer bus in some sense. So this is the kind of interpretations. Okay, so I assume that all the terms in the Hamiltonian are independent. That is just for simplicity of discussion. And actually, if it's not the case, then the way you sample the probability becomes a little bit more correlated, but that's not a big deal, I think. So this is a formal proof that the 2D toric code is not thermally stable at finite temperature. Interestingly, you can use this kind of argument in 3D toric code, and you can also prove that the 3D toric code is not thermally stable. But in 4D, you can prove that 4D toric code is actually thermally stable in the sense that there should be no short depth quantum circuit to prepare the Gibbs ensemble. And this is consistent with the fact that 4D toric code is a self-correcting quantum memory in a sense that memory time is very big, exponentially big.
So if you go to 5D, would that be stable, or 4D is?
5D, 6D, 7D, yes. Any dimensions higher than 3, yes.
Then 3 is stable.
Mm-hmm. Right. So this question is still like very interesting and it's open in a sense that, so for example, around 2 or 3 years ago, I proved that this fractal model, this fractal topological order model, that was a candidate model of a self-correcting quantum memory. I showed that there is actually an efficient way of preparing rho beta. And it's actually my version required log L square depth, square of log L, but still I think log is like constant. So, but still we don't know if there exists some nice 3D Hamiltonian whose Gibbs ensemble is thermally stable at finite temperature or not. Okay. Any other question? Yes?
So like, if you do find a 3D code that is thermally stable, that would imply it may have the quantum memory.
Yeah. Yeah, hopefully. Yeah, I believe so. I mean, there is no formal proof, but it is very likely.
I'm just saying, like, is there like a deeper reason why we believe that's true, though?
Deeper reason. So far, I think there is this nice analogy between this static property and dynamical properties, and then the way you can prove this thermal instability of toric code sort of has a flavor of the presence of a thermal bath. So in some sense, you can imagine that the thermal bath is somehow smart enough that they are actually doing this naturally. Because if it's a short depth circuit, then environment, definitely there are some probability of the environment doing this disentangling procedure to bring you to a useless, classical ensemble. So, and classical ensemble cannot store any quantum information. So, but of course, yes, formal approach is missing right now.
But also, would this imply that if this is true, then in order for us to use like a useful code, we would also have to have very high complexity to prepare these states.
Right.
So that's not helpful also, though.
Well, sure, but that's the question of how to efficiently prepare the toric code ground state. Well, it's still order n, well, square root of n, so it's efficient, right? It's doable. That we are looking for, presumably we are looking for exponential improvement of computations. So it's still fine, I think, at the level of theory. But I mean, no one has built a big toric code yet. I mean, there are some small systems, but so of course it raises another important question, that is, suppose you somehow created a toric code, and if you showed me, then if you claim that it is a toric code, then I need to verify it, and it's very difficult to verify it because, I mean, no local measurement would tell me that it is quantum error correcting code. So that's another very big question. But that is the reason why the quantum error correcting code is stable, even if it couples to the, error axon. So, if error can steal the information easily, then it's not useful. In some sense, we are also an error trying to read out the information. Yeah. Anyway, any questions? Yeah, okay. I think if not, we can just stop here.